Okay, chemists, in this last lesson, we are going to look at phase diagrams, which are what these diagrams right in front of you represent. These show a plot of pressure versus temperature for a given substance. Right now, we're just looking at single pure substances. There are other phase diagrams for binary and ternary substances, but we're looking at them for just a pure substance. So here's one for water, here's one for carbon dioxide, and they break up into sections of solid, liquid, and gas. So that's what they're showing here. There's where the solid range is, the liquid range, and the gaseous or vapor region is. And there's just 2 points I want to highlight in each of these graphs. One is the intersection of those lines, which happens to be called the triple point. And the other one is where the liquid vapor line sort of seems to veer off into space and sort of just end. That's called the critical point. So let me define both of those, and then I'll even show you an animation of one of those. The triple point is where all phases, and I'm going to say end phase changes, coexist. It is a very specific temperature and pressure for a given substance where you get solid, liquid, and gas all at the same time, but more importantly, where all the phase changes are happening at the same time. Normally you only have the equilibrium of either direction of one phase change happening. For example, solid to liquid melting and liquid to solid freezing happens along this line at some temperature relative to some pressure. Likewise, solid and vapor, you have sublimation and deposition occurring along this line. But at the triple point, you get everything. You get all the phase changes. That's hard to simulate, so I have a video that shows this with tert-butyl alcohol. This is a flask of T-butyl alcohol subjected to low pressure, and as you can see, it's starting to solidify. So we're getting freezing, liquid turning into solid, and then reversibly, solid turning into liquid. But now you're also seeing boiling. So every phase change that's possible is happening here because they've got it down to the triple point. T-butyl alcohol has a triple point at about 20 degrees Celsius, but the pressure is down at around 30 torr or so. So very, very low pressure. What we can't see in the picture is that there's a vacuum connected to this. So I've got boiling and condensation and freezing and melting and sublimation and deposition all happening at the same specific temperature and pressure. That's what a triple point is, very specific for a given substance. What about the critical point? What does that look like? The critical point is where the liquid and gas become indistinguishable. And it's not really the point that I care about, but it's the beginning of every temperature that's greater than this and every pressure that's greater than this. So it's the entire upper right corner of this phase diagram. You enter essentially another phase. You get what's called a supercritical fluid. It's neither gas nor liquid. It's very hot and high pressure. So it's heated up a lot, but compressed to the point that it can't actually vaporize. But it's so hot, it doesn't really look like a liquid anymore either. So these have pretty unique properties. They're quite dangerous to work with because they're so hot and they're so compressed. But they have a lot of interesting applications. For example, supercritical CO2. Supercritical CO2, I'll just say e.g. supercritical CO2 is used to decaffeinate coffee. That's how they get caffeine out of naturally grown coffee. You can't grow coffee beans without the caffeine in there. It's already there. It's a naturally occurring insecticide that the plant uses. We take it out of there artificially just by washing it with supercritical CO2, and it extracts the caffeine right out of it. Okay, so those are what phase diagrams look like and a couple of points about them. I want to take a moment and zoom in on one section. I want to zoom in on the liquid vapor region and show just that part of the graph. So here's pressure versus temperature again, and just what that line might look like. I'll draw a line for water because I want to use this as an opportunity to relate it to intermolecular forces. Here's what it would look like for water. Let's draw another molecule. This is what it would look like for methanol, CH3OH. And we can get a bunch of information from a vapor pressure graph like this. First of all, what is vapor pressure? It's the amount of vapor exerted by the gas phase of something in equilibrium with its liquid. So here are 4 flasks just showing an equilibrium mixture of vapor and liquid. So vapor and liquid. And we could use this as an illustration of left to right. This is what it would look like if you were increasing the temperature. P vape increases as T increases. And that's certainly true if I look at this graph. Both of these have increases in pressure as temperature increases. And that's true for all substances. You will always have more vapor at a higher temperature. In fact, it also shows us the boiling point. The true definition of the boiling point is the temperature at which the vapor pressure is equal to whatever the surrounding vapor pressure is. So these are boiling point lines. And if we compare this with what we know from everyday life, we could draw a line where 1 atmosphere exists. I'm just being arbitrary somewhere here. And if I extend that as a horizontal just across the entire graph, where that intersects each vapor pressure curve, if you drop it down to the x-axis, you get the boiling point. So the boiling point of water, everyone should know, at 1 atmosphere is 100 Celsius. The boiling point of methanol at 1 atmosphere is quite a bit lower. It's only about 65 Celsius. So that's consistent with something we said in the previous lesson. If you have a higher vapor pressure, you actually have a lower boiling point, which brings us to the second thing I want to list over here. So P vape decreases with IMFs. And then just to follow that up, substances with high boiling point have a low vapor pressure. And you can remember that if you just think about what that means. Something that doesn't boil very easily doesn't exert a lot of vapor. It will stay in the liquid phase. Something that's vaporizing a lot will have a higher amount of vapor pressure present. Okay, so lastly, this is actually not on the AP exam, but it's the relationship between vapor pressure and temperature that is linear. Notice this is a non-linear increase up here. There is a relationship between vapor pressure and temperature that we can make linear. It's logarithmic. It's this relationship. It's the natural log of a pressure versus an inverse absolute temperature. This is called the Clausius-Clapeyron relationship. And it mathematically makes the relationship linear. It's also a way of showing how we can actually calculate a boiling point temperature at different pressures. So for example, if I want to know what temperature water would boil at if I was at a much lower pressure, so if pressure is 24.8 torr, what is the boiling point? Well, in order to use that Clausius-Clapeyron relationship, I need another reference point. Well, we know that at room pressure, which is 760 torr, The boiling point of water is 100 Celsius, which is 373 Kelvin. So I can use the Clausius-Clapeyron and substitute everything. So the natural log of the ratio, I'll do 24.8 over 760 is equal to, that says delta H vape. That means the heat of vaporization, which is 43.9 kilojoules. I'm going to write that as 43,900 joules per mole. That's because the R value is 8.314 joules per Kelvin mole. And then times the difference in the inverse pressures, which will be 1 over 373 minus 1 over some unknown. And now it's just a task of calculator skills to see what the final temperature is. By the way, if you flip these pressures, that's perfectly fine. You would just flip the temperatures and you would get the same outcome. The temperature ends up being just below 300 Kelvin. You get about 299.7 Kelvin, which is only a little bit above room temperature, 26.7 degrees Celsius. So if I had a sample of water and I reduced its pressure down to only 24 torr, I could see it boil in front of me if it was just a hot day in that particular room. Okay, so that's how vapor pressure works, and it varies with temperature and relates to all the kinds of phase changes, and that wraps up this unit.